I'm Luke, the one who represents the force on the basketball team. Double meaning right there. You see me on such fine, quality, epic basketball training videos such as how to deal with your opponent on a one-on-one dunking contest, and I couldn't have done it without my peeps on the b-ball team, my backup. Part 3. Okay guys, so for this is part 2, and we're looking at polar molecules. I did spend a bunch of time in class talking about polar molecules, so let's see what we have here for that. Now, what do we mean by polar? That's the first question. Well, one side has a negative charge and the other side has a positive charge. Well, okay, what does that look like? Well, let's look at our good old-fashioned stomach acid. Hydrochloric acid, we find that in our stomachs. Now, you guys know chlorine loves electrons, and hydrogen is kind of like the little kid that just, it can get its electron taken away. Okay? So what happens? Well, you guys might remember, and this is the theory, that in a tug-of-war between chlorine and hydrogen with that electronegativity stuff, the hydrogen's electron is going more toward this end of the chlorine. Okay? It doesn't chlorine doesn't totally have ownership, but it has a lot of it. So what happens is you get what's called a partial charge. That's that funny little symbol yesterday, and you got a negative, partial, and then over here, because you don't have the electron, you get a positive, you get a partial positive. Those are the charges. So what happens is hydrogen chloride or hydrochloric acid literally is a polar molecule. Polar meaning opposites. That means there's a positive side and a negative side to it. And well, hey, what difference does that make? It makes the difference in that we need to dissolve things. We need to be able to break down things. We would also need to be able to put things together. And that polarity action, it helps. And let's face it, you know, when you have your nachos on your mom's favorite plate and you let the cheese dry on it, and you're going to spend 5 hours literally, scraping it in the kitchen sink because you know when mom gets back, she's going to be a very unhappy camper. Yeah, think about that for a moment. That's why you use something to make it easier for you. You put water in the sink, put the plate with the cheese stuck on the plate in the sink of water, and let the water do its magic. Woo! Yeah! Chemistry in the real world. Welcome to Canu's Crash Course Chem. C4. It's explosive. Okay, so now you got the idea about polarity. Well, what about nonpolar? In nonpolar, you're not really seeing this positive negative side to it. That doesn't mean it doesn't exist at all. It's just it's not there compared to something like this. Okay? So nonpolar, best way to look at it is slippery. Like oil. Oil is nonpolar. Okay? And that's why oil and water don't mix. It's kind of like UCLA and USC, they don't mix. It's like soccer players and basketball players in sixth period. They may or may not mix. It depends on the day and who's present. Yeah, I am talking about you people over in sixth period. Okay? Okay, let's move on. So, in nonpolar molecules, you have to look at the whole thing. And if it could be all positive or all negative, but it doesn't have both. That's what makes it nonpolar. So the reason why oil and water cannot mix is because water can actually surround the oil molecule, but it can't break it. That's the difference. So water can surround, yeah, water can surround the oil molecule, yeah, no problem. And you'd say, how does that apply in the real world? Well, you're cooking or baking, and let's say you get vegetable oil or canola oil or palm oil or corn oil or canola oil on your hands, and you say, oh, I gotta go wash it, and you go to the sink, you turn on the faucet, and you let the water run, and the water is not taking out the oil. Now, some of you guys are saying this is obvious. Yes, but this is chemistry in the real world. I'm actually explaining to you why, so you know. Water can't dissolve the oil. It can't break it apart. Soap can. And there's the difference. So now that you guys got the idea about polar and nonpolar, and why would that matter? Another way to look at nonpolar is think it's slippery. You know how oil is slippery. That's kind of maybe why we use that in our car engines, right? To make those pistons in the engine go more smoothly. Think about transmission fluid. Think about brake fluid, guys. That's got slippery stuff in them because that's what allows our car parts to work and allows you to get to the places where things are happening and you can hang out with your peeps and be cool all you want, right? Right. Okay, how do you tell? How do you tell if a molecule is polar or not? And some people are going, well, I remember Adam Sandler in The Wedding Singer. It's my microphone, so I'll say anything I want. Okay, that's to keep you people awake. Remember, it's not just 6th period watching this. It's other classes as well. And who knows, maybe other people on the internet. Okay. So how do you go? Seriously, how do you go and look at a molecule and tell if it's polar or nonpolar? Well, one thing, you could look at the shape and you can tell if it's linear, it could be polar, could be not polar. So what do we mean? Well, if it's like this, is this polar or nonpolar? It's going to be nonpolar because it's symmetrical. This is different. It's asymmetrical. Remember, we talked about that. So nonpolar, so I'm going to write NP for nonpolar, and here it's polar. I am not worried about how polar it is. I'm not going to worry about that. Okay? I just want you to be able to look at a molecule and be able to tell me, is it polar or nonpolar? That's it. So linear, it can go either way. Now, if it's bent, like water, or maybe SO2, okay? Those, ladies and gentlemen, are polar because you have a negative side here, and here you're going to have a negative side and a positive side here. So they're asymmetrical. So when it's bent, it's always polar and polar. Okay? All right. I'm going to give you guys a few seconds to go ahead and write that down. If you want me to pause it, let me know. And we're off. Yeah, I did that. Okay, well, what about flat triangles? The triangular planar. Not going to worry about the bell. Hey, just first period, the Imperial Guard can wait. All right, so if you look at the flat triangle, there's no unshared electrons. It's the same all the way around. It's symmetric. Guess what? It's nonpolar. It just is. On the other hand, if we look at something like ammonia, that's a pyramid. If it's a pyramid, guess what? Polar. Okay. Why is it polar? Because here it's the negative side, here is the positive side. It's asymmetrical. All right, last thing. Last thing, ladies and gentlemen. As we go through here, and that is the tetrahedral. Tetrahedral, here we go. nonpolar? Is the edge around all the same? Because if it's all the same, it's symmetrical. And if it's symmetrical, it's nonpolar. Oh, yes, nonpolar. Now, what happens if I turn around and I erase this and I put a Cl? Does it become polar or does it stay nonpolar? Look around the edges. Are all the edges the same? Yes or no? No, we got a chlorine there, and guess what? That makes it polar. Okay, so hopefully this is going to show you guys how you can look at a molecule and be able to tell if it's polar or nonpolar. Okay, and I'm hoping that this review will help you guys out. Until then, hey, there's going to be a short answer question explaining about something about the molecule shapes. But hey, we covered it. All right. I'm Luke Wooten, the force of the basketball team, signing off.